Okay, so I think today we'll probably get through the Excel file side of this, testing for normality. And then when we come back, we'll do a short PowerPoint presentation. I don't think we'll quite get to the PowerPoint presentation today. So short introduction to testing for normality. So suppose we have a population we're studying and we've taken a sample from that population. So we have a sample, X1 through Xn, a sample from the population. And we want to know, on the basis of this sample, do we think that it's reasonable to infer that the population is roughly normally distributed, or do we think it's more reasonable to infer that the population is likely not normally distributed? Why is this important? Well, one of the reasons is, just like we said up here, we suppose that men have weights that are normal with this mean and standard deviation, and we're looking at an average of size 16. Well, we're leaning pretty heavily on this presumption that the underlying distribution is normal here. If it wasn't normal, this sample of size 16 is really nowhere near the sample size of 30 that we want to satisfy our rule of thumb. We'll also see later on for some of these other sampling distributions. I was on the other page, but remember I mentioned there are different sampling distributions. Well, different sampling distribution results and different, confidence interval and hypothesis test results and so on that build off of those have different amounts of tolerances to deviation from normality, right? So I can apply this result of the central limit theorem to a population that's not normal. And even if the population deviates pretty significantly from normality, if I have n bigger or equal to 30, I can still apply this. But there are some of them, like, for instance, the sampling distribution for, say, the standard deviation or the variance, where we really have to lean heavily on the underlying population being normal for things to work out properly. And if the underlying population is non-normal, that becomes a much bigger problem in some other contexts. So we might be really interested in making an educated guess about whether or not the underlying population is normally distributed on the basis of a sample. And there are basically three approaches. And this is an increasing order of complexity. There's the so-called back of the envelope test. And it's not like the back of the envelope test, but a back of the envelope test is basically kind of a quick and dirty way to get a pretty decent idea of what's going on. That's what a back of the envelope test generally means. So it's a little reminiscent of something like, say, the range rule of thumb, right? Where we say the range is about 4 standard deviations. The standard deviation is really annoying to compute. The range is really easy to compute. So if I just say that a standard deviation is about 1/4 of the range, that's kind of a back of the envelope estimate for the standard deviation. It's quick and dirty, not super accurate, but maybe gets me in the ballpark of a right answer. Second, I can look at something called the QQ plot. And this is what we'll address in the PowerPoint presentation next time. And the third is, well, we have formal tests. So we have things like the Kolmogorov-Smirnov test, the Anderson-Darling test. There are formal tests where you do a bunch of computations, you get some number that's related to your data, you compare that to some number that's some kind of standardized number, and you see where the one number falls relative to the other, and that gives you a claim. It gives you a claim that either the population seems to be normally distributed or the population seems to not be normally distributed. we're not really going to talk about these formal tests. I'll kind of briefly give an idea of what a formal test structure like might look like when we talk about the Q plot. But for right now, we're going to focus on these back of the envelope, or this back of the envelope test idea. So what's the idea of the back of the envelope test? Well, the logic goes this way. If the population is normal, then I expect the following. I expect it to be, well, what were our three characteristics of a normal distribution? I expect it to be symmetric. I expect it to tail off to the sides. And I expect it to basically look bell-shaped. In other words, if I expect to see symmetry, I would expect that the Pearson coefficient is between -1 and 1. If I expect it to tail off, well, one way that I could think of tailing off, something that doesn't tail off to the sides, is something that has a lot of meat in the tails, far away from the center of the distribution, right? So in other words, how what percentage of my data points fall within 1 standard deviation, 2 or 3 standard deviations? I expect it to follow the 68, 95, 99.7 rule. I expect rough concordance with that rule. If I look at the proportion of data points that are within 1 standard deviation of the sample mean, 1 sample standard deviation of the sample mean, then I expect that to be about 68% of the data points, 68% of the sample size. Similarly with 2 standard deviations and 95%, 3 and 99.7%. And then bell shape, just looking at the histogram. So I say if it's normal, if the underlying population is normal, then I expect the sample to roughly follow these 3 criteria. If I see substantial deviation from these criteria, then that would lead me to conclude that the underlying population is probably not normal. Okay, so let's bring up this Excel file with some of the data and we'll investigate some of these data sets. Okay, so this first one is S&P data. These are some S&P 500 monthly returns ordered from most negative monthly return to most positive. And again, what I might want to look at is, say first the histogram. And it's a little hard to tell on a histogram like this. We can maybe split up more bins, but we do see kind of a peak in the middle and kind of a tailing off to the side. So again, this is a back of the envelope test. It's rough, it's dirty. It's not, we're not expecting a graph that's going to look like a perfect, textbook normal distribution. But does it look like it's right skewed or left skewed, or like clearly just going from bottom left to top right, or vice versa? Doesn't really look like that to me. It does look like it kind of peaks in the middle and has some tails along the sides. So I don't see any big red flags yet. I'll compute my Pearson coefficient next, looking for skewedness versus symmetry. This is 3 times the mean, which I've computed up here, minus the median, which I'll just compute in line. So 3 times mean minus median, make sure those are in parentheses, over standard deviation. Let me actually double check that I actually have the right things here. Yeah. Make sure I didn't have some vestigial mistake or something. And I see my Pearson coefficient negative 0.19 or so. That's certainly between -1 and 1. I see no evidence of skewedness. So no evidence of skewedness. The histogram looks in the ballpark of what I would expect. And then let's check the empirical normal rule. So for the different standard deviations, 1, 2, or 3 standard deviations, what's the mean minus 1 standard deviation? That's mean minus this many standard deviations. When I drag down, I want my mean to stay the same, and I want my standard deviation to stay the same. So down here, I see I have mean minus 3 standard deviations. And then for the mean plus 3 standard deviations, so mean, and I'll lock that, plus this number of standard deviations. Oh, and again, I'll drag those down, just double check, and it looks like everything worked out right. And here I'll just kind of count. So I want to count, I've already sorted them in order. So I want to count everything from negative 3.35 up to positive 4.65. So starting here and going up to there. This will just give me the number of data points that are within 1 standard deviation of the mean. And I could maybe come up with some fancy formula to type in here, but in this case, it's just easier to code it in like this. So here I want to count all the data points with value between negative 7.3 and positive 8.6. So that's everything from the lowest number up through everything from 1 below the highest. And then negative 11 to positive 12 includes everything. And the percent is this number over 23, which is our total number of data points. And then we'll just do times 100 to make it into a percent, a little easier to read. Oh, why did it do that? Excel is usually good at guessing what you want it to do, but sometimes it does crazy stuff like that. So these are the actual percent of the data points that fall within 1, 2, and 3 standard deviations. What would we expect to see? We'd expect to see 68, 95, 99.7. And that looks pretty darn good. You might say the 78 versus the 68 is maybe a little far off, but really what we're worried about here, practically speaking, what we're worried about is that we get outliers more often than we expect. We're practically not too worried that there's a little more meat near the mean. We get more worried, we experience more problems if there's too much weight in the tails, more than there should be. So what do we see? We see decent adherence to the empirical normal rule, the general kind of fit, the general, tailing off or not having too many outliers. We see lack of evidence of skewedness, so the symmetry kind of seems to be working nicely. And again, this is a very coarse histogram. If we wanted to, maybe we would split each of these bins in half or something and get something a little more refined, but the histogram looks good enough. I don't expect it to look like a perfect normal distribution with only 4 bins, but I do see that it kind of peaks in the middle, tails off to the sides. It looks very roughly in line with a bell-shaped distribution. It doesn't look bimodal. It doesn't look heavily skewed or like it's just going bottom left to top right or vice versa. So this one, I would probably say, okay, I would probably be happy calling this or happy presuming that this data set came from a normal distribution, normally distributed population, and, then being able to apply whatever results of central limit theorem or anything like that I might want to apply. And here is, for this one, I refined this a little bit for the histogram, and you can see that by using by using more bins, we get something that looks a little bit nicer. There's a little clearer of a peak in the middle and tailing off to the sides. Again, does it look like a perfect normal distribution? Well, no, of course it's not going to look like a perfect normal distribution with only a sample of size 23 or so. But does it look good enough that I can see that it's kind of more or less symmetric about a mean? The mean is about 0.65. So it's kind of more or less symmetric about these two tall peaks here. Roughly tails off to the sides and peaks in the middle. Yeah, that's probably good enough. When we come back, we'll take a look at this HIV viral load data, and we'll do the same thing with that.